Oh, I need to unmute you. Hold on. There. So try now.
Okay, can you hear me now?
Yes, I can hear you.
Okay, thanks for the introduction. So hello everyone, this is Xiaoyi. So I've been presenting, in OFED, in Open Fabric, this workshop many times. So this time I would like to present our recent work. So this is about how to design efficient user coding with SmartNIC offloading techniques on InfiniBand. So this work is done by my student Haiyang Shi. So he's a fourth-year PhD student currently. So he worked with me for last several years, and we are be happy to share our research results in this conference. So this talk is majorly based on our last year supercomputing conference paper, which is a best student paper finalist. So now let me start the presentation. Next slide, please. Yeah, also, all now we are in the area of data explosion. Data is growing and will keep growing very rapidly. Showing this figure, the annual data size increasing superlinearly as the red line shows, and it's predicted to be like 175 zettabytes by 2025. However, on the other hand, if you look at the drive costs, like hard drives or SSDs, even though the price is decreasing, but as shown in the blue lines, the price decreasing trend is to hard disk drives are still relatively slowly. So, and also because the hard drive is still the primary storage medium by today. So we believe that the total storage cost for storing all this data we generated will be very high still. So we can say that the storage is not a cheap resource anyway. This fact in turn forces us to rethink that how to design distributed storage systems to be both high performance and cost efficient. Next slide, please. So in a distributed storage system, there's some animation. Can I control it or okay? So yeah, in distributed storage system, we can choose not to use any fault-tolerant mechanisms, right? So in that way, we can keep the storage overhead at the lowest level. We call it like an OFD, which is like a high performance and high storage efficiency, right? But in this case, the system is not reliable. We will likely lose some data. So to achieve reliability, many widely used distributed storage systems adopt a technique called n-way replication. Next, please. Yes. That means the system will store like n replicas for a piece of data to tolerate up to n-1 node failures, right? However, as showing this figure, the use of replication will cause performance degradation because you have to write multiple replicas to different nodes, right? In that case, it also, of course, significantly increases the storage overhead. Now, the question is there any alternative approaches in between to reduce the storage overhead? The answer is yes, and one of them is called Erasure Coding, which is very famous technique to be used to support fault tolerance in storage systems. Next slide, please. So now let me briefly introduce EC basics, especially for read-only code. Next. Read-only code is a very famous and widely used Erasure code. It has two essential parameters, K and M. So we usually use RS like a K, M to represent the read-only code. It has been widely used in many storage systems like Microsoft Azure Storage and HDF 3.x. Now, with the configuration of K and M, the coder will generate N chunks for K data chunks, and it is able to recover the original data on any K-survived chunks when data corruption occurs. Now, let me show you one example to show how this works. So please, next. So this example for the read-only code, where K equals to 4 and M equals to 2. So basically means for encoding, the coder will use a predefined and invertible generator matrix to multiply with 4 original data chunks. So original data matrix here, as shown in this figure. And the result, next please. The result will consist of 4 data chunks, which is like original data, and 2 parity chunks. Okay, next. This is the encoding. So after encoding, then probably if this data or parity chunks are going to be distributed across multiple data nodes. Now suppose if 2 data chunks are corrupt, next, then in this case we also need to let's also remove 2 corresponding rows in the generator matrix. Next, then this equation still satisfies, right? So this matrix left side for the remaining part still equals to the right side. So next, please. Yeah, at this time, this is survived data, right? So now if we multiply the inverse matrix of the remaining generator matrix on both sides. Next. Next. Yes. So then the inverse matrix and the remaining generator matrix on the left side will be, because they will be equal to identity matrix, right? So okay, next please. In this case, the left side will become like only original data will be left. In this case, we show that we finally get original data chunks from the survived chunks with the multiply of inverse matrix with the survived data. The advantage of using EC in this case is low storage overhead for widely used configurations like RS4,2 and RS6,3. Their storage overhead is only about 1.5x compared with the corresponding 3-way replication and 4-way replication whose storage overhead as high as 3x or 4x. This is much better, right? The efficiency is much better. So next. Okay, so now let's have a quick look on how this EC works in distributed storage systems, especially in the read and the write operations. For write, whenever the client get enough data chunks, next please. It will encode on them. It will encode on them to generate parity chunks. Next. Yeah, so the original chunks in this figure are represented by the blue box, and then red one are parity chunks, right? Now, once you have this encoded data, like 5 chunks, you have to distribute them to 5 nodes. Next. Yes, so this is typically how write works during the encoding stage. And now if you look at the read, for read, if the client notice that there are data corruptions, it will fetch survived data and the parity chunks. Decode on them to recover the original data chunks. Next. Okay, so now we know how EC works and also observe that using EC. Next, please. Because in the client side or in the writer or reader side, there's both computation, right? And this arrows basically means communication. Next, please. So explain EC will introduce both computation overhead as well as communication overhead. Basically means this is both computation and the communication intensive workload. Okay, next one, please. Go. Next. So the question is, are there good approaches to improve EC performance? Yes, of course, in the community, there are different ways to improve EC performance. So somebody utilize like SMD approaches on CPUs to accelerate EC operations, and some of them use GPUs. So for this community, we particularly interested with how to offload EC on SmartNICs, right? So now let me introduce what kind of techniques or what kind of mechanisms are available in the current SmartNICs. Go ahead, next. Through our exploration, we found that currently we have promising capabilities on modern SmartNICs, especially like MLNX InfiniBand connects X4 or later, like 5, 6. And because many top 500 clusters are using InfiniBand NICs or Rocky, those kind of NICs. So these are becoming a potential very, very good platforms to utilize and to improve the performance of EC operations for distributed storage systems. Because SmartNICs, we can both potentially offload the computation and communication on the device. The EC offload feature is available and that will be available in many advanced SmartNICs in the future. Next one. This figure actually shows the state-of-the-art EC offload capabilities on modern SmartNICs, and broadly it can be classified into two classes. One we call like incoherent EC calculation and networking, and the other one called coherent EC calculation and networking. As illustrated by the left-hand side figure, this is incoherent EC calculation and networking. The initiator has to post-send and post-EC operation multiple times. On the other hand, with coherent EC calculation and networking, the initiator only needs to post one EC and send to complete the same goal, such that coherent EC calculation and the networking feature involves less CPU time than the incoherent one. Another potential advantage, of course, here is that for coherent EC calculation networking, it may only have less DMA operations. Next. So based on our understanding, the implementation of coherent EC calculation and networking has the potential to reduce the DMA operations significantly. Next one. Now the question is, given the promising coherent EC calculation and networking capability available in the SmartNICs, let's review the traditional EC paradigm to use this feature in the storage system. For encoding, could you please just show all the things, yes, in this slides, because I have a lot of animation. I don't know, I can't control this figure, this animations. That's not easy. Yeah. Show again. Next. Okay. So for encoding, right, after the client collects K data chunks, we will post its encode and send, such that its NIC gets these data chunks, encode on them to generate M parity chunks, and send data to the parity chunks to data nodes. A cluster using this paradigm can be split into two sets. One is like just do the EC, and the other set is do the receiving kind of things. So if we consider the cluster as a graph, we call it or we label it as a bipartite graph-based EC paradigm. So basically, we see that traditional EC paradigm on SmartNICs actually follows this bipartite graph architecture. Next one, please. Similarly, for decoding, the client fetches K healthy chunks from survived data nodes. Next. Then next. To reconstruct the cropped chunks, and the cluster can be split into two sets as well. Next. Next. Yeah. Again, this still for the decoding process still follows bipartite graph-based EC paradigm. Now the question is, what kind of limitations are there for this traditional bipartite graph-based EC paradigm, and what kind of challenges to improve it? Next, please. Next. Yes. So the first limitation is we observe that if we follow this kind of approach, is like the EC operation will actually lose a lot of opportunities to achieve better parallelism. As we can see from the encoding and decoding examples, EC calculation is only performed by one node or by one NIC, and then the other involved nodes do not carry out any computations. They just wait on the parity chunk or data chunk. So the first limitation of BiEC is lack of parallelism, and the limitation two is that if you look at the current designs, we see that the driver or the OFED still treat a NIC as a power processor, not fully exploit network resources. Next one, please. We also found another limitation of existing APIs that currently the SmartNICs drivers only support encode and send primitive, and there's no support for receiving decode, which is also needed and widely used for the storage systems. So next, please. To summarize the challenges that we listed at least 4 of them here. So can we firstly propose a better EC paradigm, which is able to exploit the network resources in an optimal manner? And if such an EC paradigm exists, how can we achieve better overlapping? And the third one is, can such a new EC paradigm be applied uniformly for both encoding and decoding procedures? And then, are there any additional challenges to co-design applications with the proposed EC paradigm? So now let me briefly introduce what kind of ideas we have. So the key observation is that instead of offload the EC operations to a NIC and use the NIC as another kind of processor, we should actually decompose the EC computation into multiple or sub EC calculations, which then are possible to be performed on a set of nodes in parallel rather than on one NIC, right? So the bipartite EC graph can be transformed to another. If we can add another layer of nodes, then the data can be transformed to tripartite EC graph. We name it tripartite graph-based EC paradigm. So next, please. So this slides actually show how it works. Basically, for the node in the layer 1, it just sends the data chunks to each node, and then for the node in layer 2, they just do the sub computation on this one chunk, and then generated some parity chunks, sub parity chunks, and then the node in layer 3 just aggregate these parity chunks and then do the XOR on that, then finally you can generate the final parity chunks. So this is the way how we split the bipartite graph for encoding to a 3-layer, which is a tripartite graph. Okay, so the example of the TriEC for encoding and the decoding, that actually both of them, these slides have shown the decoding procedure. Okay, next please. Yes, for instance, the data node in layer 3 will firstly decodes to generate P intermediate chunks, and then data nodes in layer 2 will fetch these K intermediate chunks and sums them to reconstruct wrapped chunks. And then clients in layer 1 just can get the recovered chunks finally. So both of these examples actually show that for the encoding and the decoding, TriEC can be uniformly applied to both these two processes. Okay, so next one, please. So now this is just the basic idea about the TriEC, right? How to apply this idea to the EC operations. Now let's see how we can actually use these techniques to the real storage systems. We choose Memcached as an example. So basically, we can this is based on Memcached 1.5.12. We choose an interleaved architecture. Basically, we divide the nodes to EC groups. In each group, there's a leader and data processes and the parity processes. And then with this interleaved architecture, we are able to balance the workloads like the data process and the parity process to different nodes evenly. So this is the best way to utilize the resources of the cluster. The next one. So now let's see how it works for different operations. TriEC-Cache basically supports 2 operations, set and get. In these slides, we briefly show how set and get works. For a set operation, the leader splits the value into 3 data chunks and send them out. Each data process encodes on the received data chunk to generate intermediate chunks, as we discussed before, and send them to the parity processes. After receiving enough intermediate chunks, each parity process sums them up to generate the parity chunk. And then for get operation, if there is no data corruption, the leader just fetches those data chunks and return them back to the client. But for get operation with erasures, like there's some corruption happens, then the leader will fetch from the data processes, and the data process who has corrupt data chunk will start to recover. It fetches the intermediate chunks from healthy node and the parity processes, and then sums them up and then gets the recovered data chunk, then send it back to the leader. And then the leader will have the final recovered chunk, and which can be returned to client. So this is how it works with the Memcached architecture. And then for get operation, of course, we also implemented the receive and the decode primitive, which is missing in the existing OFED. So next one. So another interesting thing we observed during our co-design with Memcached or with TriEC-Cache is that we find with TriEC we automatically got another very powerful and advanced feature which is called in-band recovery. So showing these two figures, the left side is the traditional approach how you can do decode. So basically you have one node and then you fetch the survived data, and then you do the decode on this node, and then you get the recovered data, right? But unfortunately, the unhealthy node still unrecovered. In that way, you have to design another approach, like write back or recover in the background thread to recover that unhealthy nodes. However, with our TriEC architecture, during these processes, for the nodes which have data corruption, they are able to automatically recover their data during these processes. So we call it in-band recovery. There's no extra computations or computation needed for those nodes be recovered. Next one. Another interesting thing is we see the optimization opportunities within the MLNX OFED currently. For instance, based on current APIs available in the OFED, we see that there's probably some possible overhead if you don't implement it carefully. So for instance, we should try to avoid the sending of unrequested chunks. In this way, you can save some bandwidth and get better performance. Another important thing is the EC calculator cache. So basically means that if you initialize the EC calculators every time, it's very expensive with MLNX EC Offload APIs. So the traditional idea is kind of, if you can do cache, that's definitely better, just like we typically do registration cache for RDMA, right? Similarly, you can do cache for EC calculators. So that, of course, you can do dynamic cache or you can do static cache, right? So based on your application workloads and what kind of, how much reused structures can be done, you can choose either way of that. Next. And this actually, the right side figures show that with cache, you can save a lot of performance. Okay, now let's see some benchmark results. This is a micro-benchmark we designed to show that how if you can run different kind of configurations of radial code with the driver, with the OFED, then what kind of performance you can get. Here we compare BiEC and TriEC. We see that from 512 bytes to 8 megabytes chunk sizes, we are able to see a very good performance improvement from 23.5 to 45.1%. This reduction for the latency. Next one. That's for encoding. Then for decode, that's for encoding with RS. I think that is 12,4. And then somebody will say, okay, maybe I'm using different kind of configurations with Erasure Coding, right? 3,2, 6,3, 8,3, or 10,4, right? So in that case, we actually uniformly evaluated with different configurations with different chunk sizes. We see that for different configuration, we see different improvements. For instance, for 3,2, we see 1.29 x speed up, and then for the last one, like 10,4, we are able to achieve up to 1.72 x speed up. These are all widely used EC configurations in the storage systems. Next one. We also did the comparison for the decoding processes. So this graph shows that also from 512 chunk size to 8 megabytes chunk sizes, this is the RS 12,4. We see the TriEC is able to reduce the decoding time by 18.6% to 64.6%. Next one. And we also systematically evaluated with different configurations like 3,2, 6,3, 8,3, 10,4. All these are widely used these configurations for decoding. And then for decoding, just because of the benefit like the in-band recovery as well as some optimization we did, we see a much better performance improvement. This is like 2.3, 2.3, 2.2, 2.1, 2.1 for different configurations. So we also evaluate with the micro applications benchmarks like YCSB. So here we run the YCSB with different kind of configurations like 50 to 50 write to compare with read, and then 95 to 5 and then 100 only read some those kind of workloads. And then we actually mimic the real scenarios on 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 distributed storage systems, we only inject 1% of the failures, and also we follow the weighable distribution of these failures. So we can see that on this kind of real scenarios, which we mimic, TriEC is able to speed up the overall throughput performance by up to 13% for equal shares, or 15% for read mostly, and 40% for read only workloads. So next one. Yeah, with this, let me conclude our talk here, and then we give some time for the questions. So in this talk, we basically trying to propose or introduce a new EC NIC offload paradigm based on the tripartite graph model, which we named it TriEC. So compared with BiEC, we see that TriEC has much better performance for both latency and throughput. And then we also introduce a new receive and decode primitive on top of MLNX EC NIC offload APIs. We co-designed the TriEC with a key-value store based on Memcached. We show that this kind of schemes can really help for some real key-value store or storage workloads. In the future, we also plan to apply TriEC to other storage systems and hardware platforms. So if you have interest to get more details of how we design this work and what kind of other benefits can be achieved, and so we have very interesting proofs of some theorems on how, in what kind of conditions TriEC can outperform BiEC. Then you can read our paper in SC 2019. As I mentioned, it's a best student friendly list. Please feel free to read it, and if you have any questions, I'll be happy to be contacted, and I'll be happy to answer those questions. Next one, please. Yeah, of course, let me thanks to many of our supporters. For instance, for Ohio Supercomputer Centers, they are very kindly provided the cluster access, so we are able to double check our results on real HPC clusters. And then we also thank MLNX for donating some SmartNICs for us to do the initial design. We also thank the reviewers for their feedback and this work, and also of course we sent NSF. Next. So with this, let me stop here, and then I will be very happy to answer any questions. Thank you a lot.
Thank you, Xiaoyi. Let's see if you have any questions. Let's see. Okay, audience, any questions for Xiaoyi before we end today's Day 2 virtual workshop?
Yeah, 2 questions. Could you please back up to the slide where you are moving the data from in the matrix on the right? Keep going backward. Keep there, right there. In the top set value, you are writing the data to node 1 and node 2 and node 3, and then you are calculating the EC information from the data in node 2 and node 3. Is that correct?
For the decoding, right?
For encoding.
Yeah, for encoding. So for encoding, the leader, like node 1, will send the data to node 2 and node 3, right? And then of course, node 1 itself will also have 1 chunk left, but that's local, right? So this is logic. This is like a logical view. So that chunk you don't have to really complicate. You can store just in the memory. And then for the layers 2, then node 1, node 2, node 3 will do some EC calculations on their own chunks like D1, D2, D3 separately or in parallel, and then those sub calculations will be done in parallel, and then they will generate some intermediate chunks which will send to node 4 and node 5. And then node 4 and node 5 will fetch these data, will get this data and do final calculation to generate the final parity chunks, which will be stored on node 4 and node 5, which is the P2, right. P1 and P2.
So what happens if the data is corrupted in its initial transfer from its origin into node 2 or node 3, and the EC protection information is calculated based on corrupt data, as compared to calculating all of the EC information in the original buffers on the original node and then transferring them all in parallel?
Yes, so this is a very good question. This is kind of how basically it's like if there's a failure happening in between, right? What happens, right?
Right. EC is designed to protect against the failure that you're exposing yourself to.
Yes, that's true. So for this question, what we did is we achieved this one in the TriEC-Cache layer. So basically, if there's any crash or is any error happened unexpected during these processes, then this nodes will report these errors to the leader, and the leader will send the failure back to the client, and then client will issue another operation. So currently we did it in this way. So because even for the default BiEC approaches, if some internal error happens, it also report errors, right? They cannot automatically do something at this point. So this actually will be easier be done in the runtime or in the library rather than in OFED. Right? So that is what we did.
Yeah, that means you have to trust the transport to transport the data and respond and acknowledge success or failure. And you cannot trust your EC mechanism for data transfer. So I don't think that the model holds. The second question I have is related to the latencies that you're reporting. Are you reporting latencies end to end? In other words, transferring from the origin node to all of the destinations 1, 2, and 3, and then also to the node 4 and 5? The final calculations and then an acknowledgement synchronously back? Or are you calculating your latencies in the subsequent graphs just based on the data landing in nodes 1, 2, and 3?
This is the blocking operation code. So this is the end-to-end latency. So everything is done.
Yeah, so I don't understand how latency can be reduced when everything is a 2-hop compared to a 1-hop approach where you have to transfer things across the network twice in both directions to achieve the goal. There's something wrong with your data, or the data is misrepresenting what's really happening.
The reason is because the EC calculation is time consuming. If you know that if you do some experiments, you will see that if you are going to calculate some EC operations on a big matrix, it's very time consuming. It's much longer than the communication time. If you choose high speed interconnect, that's why
but you're calculating EC in node 1 and in node 2 and in node 3, and then you're transferring that to node 4 and node 5. We're also calculating across that the sum of those, and then you're acking back through all of those nodes to its origin. You're actually performing more EC calculations in this model than you're performing in the other. You are performing them in parallel, but that's not an architectural limitation of the design. That's an architectural limitation of the processing elements that are being used.
I understand your question, but the problem is think about if you can, just like this basic parallelism concept, right? If you can do smaller problems in 1 NIC and in 3 NICs in parallel, which is much faster, you do that one sequentially in 1 NIC. Right? And also, I want to explain that for instance, for the EC calculations, if you only do with smaller matrices, it's much faster than with a huge matrix. This is one thing. And secondly, for parallel chunks, even though there are some small calculations at the end, but just XOR operation, which is very fast.
I understand your position. That's all I really have to say.
Yeah.
Thank you.
Okay, thank you.
All right, we are over time. Few reminders before you all leave for today. Tomorrow's agenda is also similar to today. We have few sessions with a break built in. Very interesting sessions coming from our partner organizations and Ohio State also. There is a session about how to debug, and there is a demo included in one of the sessions. So it's exciting. Just feel free to dial in at around 8 a.m., though your calendar shows 7:30, because 8 a.m. is when officially the program begins. In the comments chat window, I did put in a link for the survey for today's presentation. Please, when you have a moment, give us feedback on how we did today. Thank you very much. I hope to see you all tomorrow again at 8 a.m. Thank you.